So we are going to look at a couple of quick examples. We're going to find the absolute extrema of each function on the open interval 0 to infinity. So when we say 0 to infinity, that is an open interval. Or even if we had said negative infinity to positive infinity, that is also an open interval. So we're talking about open intervals here. And the first function we'll work with is 12 minus x minus 5 over x. Well, okay, I want to find the absolute extrema. I start by saying I want to find my critical numbers on this open interval. So I want the derivative. I'm going to, first of all, just rewrite this function so that it's easier to work with. 12 minus x minus 5x to the minus 1 power. So that when I take my derivative, f prime, let's see, derivative of 12, that would be 0. Derivative of negative x is negative 1 plus 5x raised to the negative 2 power, or negative 1 plus 5 over x squared. So this is my first derivative. I'm going to use it to find my critical numbers. So let's see. Let's take this and set it equal to 0. Negative 1 plus 5 over x squared is equal to 0. So 5 over x squared equals 1. I need to get this x squared out of the denominator, so I'll multiply both sides by x squared. That gives me 5 equals x squared. And when I take the square root, I end up with x equals plus or minus square root of 5. So I actually have two critical numbers in there, which is positive 5 and negative 5. Oops, negative radical 5, excuse me. Which this seems bad, because our whole theorem here relied on the fact that we had exactly one critical number. And if we have more than one critical number, then all bets are off. But remember the interval that we're working on. We're working on 0 to infinity here. Negative square root of 5. Now I don't know exactly what that number is, but I know it's a negative number. That's certainly not between negative infinity to positive infinity. So if we're only looking at this interval, and we basically get to ignore that possibility. Negative square root of 5, that's not a problem for us. So square root of 5, that appears to be our only critical number, which is good. But remember, we also need to consider places where f prime of x does not exist. This theorem, we wouldn't be able to use the second derivative if we had a point where x is not, or where our function is not differentiable at. But it is possible for it to still be a critical point, and that would mess with my theorem. Then I'd have more than one critical number. So I need to look at my derivative, which is negative 1 plus 5 over x squared. I know that that's going to be a problem if the denominator, x squared, is equal to 0. So that gives me x equals 0. And I don't need to worry about that for two reasons. First of all, it's not in my interval. It's not between 0 to infinity. So I know that x equals 0. I don't really need to worry about it. And then the other reason is if you look back at your original function, that function doesn't exist at 0. You have a vertical asymptote at x equals 0. It's not in the domain of our function. And if it's not in the domain, it can't be a critical number. So x equals square root of 5, that is our only critical number. So this is good so far. Now I'm going to see, okay, at this one single critical number, do I have an absolute maximum? Do I have an absolute minimum? For that, you can honestly use either the first or the second derivative test. I'm going to use the second derivative test just because I think it's easier here in this case. So I want the derivative of negative 1 plus 5x to the minus 2. I'm going to do that in red right here. F double prime of x, so the derivative of negative 1, that's just 0. Derivative of 5x to the negative 2, this is going to be negative 10x to the negative 3 power, or negative 10 over x cubed. So I want to take, let's see, square root of 5 and plug it into my second derivative, check the sign. Is it positive or is it negative? So f double prime of square root of 5 is equal to negative 10 over square root of 5 raised to the third power, which this is going to be an ugly number. It's going to be negative 10 over, if you really wanted to simplify it, it would be 5 square root of 5, and then you could get an ugly decimal. Remember, it's the sign that I really care about. I have a negative 10 divided by a positive 5 square root of 5. I essentially have a negative number divided by a positive number. It's going to give me back a negative number. What does that mean then? That negative number, I'm going to go up here for a second. That negative number tells me my function is concave downward because we were talking about the second derivative. So we must have a maximum. So that means at x equals square root of 5, I have an absolute maximum. So if I wanted to talk about the absolute maximum, or actually say what it is, I have an absolute maximum at f of square root of 5, and then I'll take square root of 5, plug that into my original function, because remember, that's what tells me the y value, and that's actually what we're talking about when we talk about absolute extrema. So this would be 12 minus square root of 5 minus 5 over square root of 5. Boy, that's just an ugly number. I think I'm just going to leave it like that. So I have an absolute maximum at square root of 5, and its value is 12 minus square root of 5 minus 5 square root of 5. That is the absolute maximum on, remember, we're only working on the interval 0 to infinity. We don't get to say that it's the absolute maximum for negative infinity to positive infinity. Now, it could be the absolute maximum. If we looked at the graph, we could probably find that out, but we don't know for certain. And so for now, we can just say, well, that's the absolute maximum, and then maybe I'll even add that in on 0 to infinity. Let's look at one more example here. Here I have f of x equals 5 natural log of x minus x. So again, I'm finding extrema, so I want to start by finding my critical points, which means I need my first derivative, f prime of x. So derivative of 5 natural log of x is 5 over x minus 1. So here is my first derivative. I want to take my first derivative, 5 over x minus 1, set it equal to 0. So let's see, we'll add 1, 5 over x, that's equal to 1. So I end up with x equals 5. What else, what else, what else? I need to consider, where is my derivative undefined? Where does it not exist? For that, I'm worried about my denominator once again. If x is equal to 0, this looks bad because I have two critical numbers, or what looks like two critical numbers. But remember, 0 is not in the domain of natural log of x, which means that 0 is not a critical number. We also could have gone back and looked at the directions again. I'm just going to re-highlight it here. We said 0 to infinity. Right there, that's our interval. 0 is not strictly between 0 to infinity because we're not including 0. We're working on this open interval. So this is good. We have our one single critical number, which is what we wanted. So now I just need to figure out, do I have an absolute maximum or do I have an absolute minimum? So I want to take my second derivative, f double prime of x. And right now, as it's currently written, I would need to use the quotient rule. I don't really want to do that, so let me rewrite it. This is 5x to the minus 1 minus 1. So I want the derivative of this function. This would be negative 5x to the negative 2 power. Derivative of negative 1, that's just 0. So really, negative 5 over x squared. We'll take the critical number that we found, which is 5, plug that into our second derivative, so f double prime of 5 is negative 5 over 5 squared, which would end up being negative 1/5. which, again, it's really the sign that we care about, right? So this, okay, I ended up with a negative number. We're talking about the second derivative, so that tells me that my function is concave downward. What do I have? Well, I have another local, this time absolute maximum. Remember, we want to make the strongest statement here that we can. So that means that f of 5, I'm going to take this, plug this back into my function f of x. F of 5, this is equal to 5 natural log of 5 minus 5. That's an ugly number again. Can't really do anything with that. But we know that this is the location of an absolute maximum here. This is the location of an absolute maximum. So unfortunately, it's a lot more difficult for us to find these absolute extrema on an open interval. But as long as we have that one single critical value, then we get to say, okay, it's no longer just a local extreme value. It's no longer just a local maximum or a local minimum. In that case, if we have the one single critical point, then we get to say that that is a absolute maximum or an absolute minimum.